Welcome to this explainer on the science behind staple motifs. Today, we're cracking open a massive 30-year-old nanoscale chemistry cold case. We're talking about how self-assembled monolayers actually bond to gold surfaces. It's this incredibly fascinating journey of microscopic scientific deduction, and we're going to break the whole thing down step by step. So let's just jump right in with a fundamental question. How do you perfectly coat a piece of gold with exactly one single layer of molecules? I mean, imagine trying to tile a floor at the atomic level, where literally a single mistake ruins the entire surface. This kind of nanotech marvel is what lets us tweak metal properties for everything from biomedical sensors to advanced electronics. But for decades, the exact mechanics of how this actually happens just completely puzzled the brightest minds in science. To get our bearings, we're talking about self-assembled monolayers, or SAMs. Basically, these are organic molecules that inherently just know how to bind to a surface and self-regulate, stopping perfectly at exactly one single molecular layer. The classic, most widely studied system involves chemosorbed alkyl thiolates on gold. Put simply, these are sulfur-based carbon chains that attach themselves to a gold surface. And at exactly 1/3 of a monolayer of coverage, they perfectly, seamlessly self-regulate. But how? Well, for nearly 30 years, the scientific community relied on a massively oversimplified model. Theorists just assumed that single thiolate molecules, represented by those blue sulfur head groups, bound directly to flat, high-symmetry hollow sites on a perfect gold surface. They thought it formed this basic, predictable hexagonal pattern. It looked neat, it looked clean, and it was entirely straightforward. But there was a huge problem. The theoretical assumptions in that oversimplified model completely clashed with the actual microscopic evidence. When scientists used scanning tunneling microscopy, or STM, to look at the physical atomic surface, they found glaring anomalies. Specifically, right along the boundaries of these molecular domains, they observed tiny pits, missing atoms, exactly one layer of gold deep. It looked as if gold atoms were being inexplicably ripped directly out of the surface by the monolayer itself. A flat, static gold surface simply couldn't explain a crime scene like this. And that brings us to the climax of our little detective story. In 2006, a dramatic discovery completely rewrote the textbooks: the staple motif, chemically written as RSAUSR. Instead of a single sulfur molecule just attaching to a flat piece of gold, two thiolate molecules literally pull a single gold atom, an atom, right out of the surface. They share it between them, kind of like a staple holding a stack of paper together. This 2006 discovery by Maximovich and his team carried massive historical weight. The literature explicitly noted that methylthiolate species on AU111 are linked by AU atoms, forming this brand new RSAUSR motif. And this was a total game changer. It shifted the entire paradigm. Suddenly, the gold surface was no longer this passive, static floor for molecules to stand on. No, it was an active participant. Gold atoms were being physically incorporated right into the molecular monolayer. So what's actually happening at the microscopic level? Basically, it's an incredible electrostatic tug of war. The gold atom creates this really powerful electrostatic attraction, pulling the sulfur atoms together into rows. But simultaneously, those negatively charged sulfur atoms absolutely hate being next to each other. Think of them like terrible microscopic roommates. They create a massive electrostatic repulsion, constantly trying to push those rows apart. Let's break that tug-of-war down just a bit more. The sulfur-gold attraction acts almost like an ionic bond, which promotes the formation of nice, straight molecular rows. But that sulfur-sulfur repulsion is fighting it, trying to keep those same rows as far apart as physically possible. Now, with short carbon chains, they just don't have the physical mass to generate stabilizing van der Waals forces to overcome this. So the only thing keeping them together is sheer surface pressure. As the coverage increases to its absolute maximum of 1/3 of a monolayer, that intense compression literally forces these repelling rows into a highly specific, staggered pattern just to survive the squeeze. Because of that immense pressure, short-chain methylthiolate compresses perfectly into what we call a stable 3x4 phase. So instead of that basic hexagonal structure that scientists incorrectly assumed for decades, the molecules arrange themselves into this beautifully staggered layout. The rows purposefully stagger themselves to minimize all that repulsive energy between the sulfur atoms, while still holding on to their stable bonds. And honestly, here is the real kicker. This isn't just some isolated anomaly for a single type of molecule. Whether you're dealing with methylphthalate, ethylphthalate, or propylphthalate, all of these short-chain molecules uniformly assemble into this exact same 3 by 4 phase. This universality proved, beyond a shadow of a doubt, that the staple motif completely dictates short-chain molecular structures on gold. Okay, so the fundamental structure is solved. But we still had another piece of evidence at the crime scene. STM images were consistently showing this bizarre height anomaly. Exactly half of the identical molecules in the monolayer appeared to be precisely 0.05 nanometers taller than their immediate neighbors. I mean, it's a mind-bogglingly small detail, but the old model totally failed to explain why completely identical molecules would ever sit at different heights. Well, the staple motif elegantly solves this mystery too. Because the motif binds molecules in pairs, sharing that single gold atom, the actual geometry of the arrangement physically forces one carbon chain to sit slightly closer to a neighboring gold atom than the other. Because of this extremely specific microscopic environment, that particular chain physically cannot tilt as much. And because it tilts less, it stands up straighter, making it appear just a tiny fraction taller under the STM microscope. Boom, mystery solved. Now, you might be wondering, what happens if we relieve the pressure? If we reduce the coverage to slightly below that maximum 1/3 monolayer, the molecules immediately give in to that sulfur-sulfur repulsion we were talking about earlier. They literally stretch out into these beautiful, evenly spaced parallel stripes all across the gold surface. This entire phase transition process happens in highly predictable, almost mechanical steps. At full saturation, you've got the tightly packed 3 by 4 phase. But drop the coverage slightly to 0.27, and they breathe out into moderate striped phases. Drop it even lower, down to 0.11, and the distance between the stripes actually scales directly with the physical length of the carbon chains. As the pressure drops, the staggered rows just smoothly straighten out into distinct, separate lines. But what about longer molecules? Pretty much everything we've covered so far has focused entirely on short chains, which are governed almost exclusively by electrostatic forces. But when we start looking at longer chains, things like butanethiol and octanethiol, the sheer physical mass of all those extra carbon atoms introduces a massive new force to our equation, van der Waals interactions. These are the physical attractive forces between the larger carbon chains themselves. And this shift is the true tipping point. For short chains, right up to propylthiocarbonate, electrostatic bonding dominates, giving us our trusty 3 by 4 phase. But adding literally just one more carbon atom, moving up to a butyl chain, completely tips the scale. The physical van der Waals forces between these longer chains just totally overpower the underlying electrostatics. This shifts the entire saturation structure into a significantly more complex phase, known as the 3 by 2 √3 rectangular phase. So you might be wondering, does the staple motif even still exist in these long chain phases? The answer is a resounding yes, and we actually have the final proof. Even under the total dominance of van der Waals forces, STM images of long-chain octanethiol reveal highly unique, zigzag-shaped domain boundaries. A standard individual molecule model simply cannot create a pattern like that. Only the paired RS-AU-SR staple motif naturally locks together to form these very specific 1-2 zigzag shapes. It's essentially the undeniable fingerprint of the staple motif. All right, let's tie this whole shebang together into a unified nanoscale model. The discovery of the RS-AU-SR staple motif as the universal building block is absolutely revolutionary. In one single stroke, it solved 30 years of confusing height anomalies. It explained the missing gold atoms and the mysterious pits. It perfectly predicted both the 3 by 4 phases of the short chains and the complex stripe phases. And it beautifully balances that whole tug-of-war between electrostatics and van der Waals forces. Basically, it means we finally, truly understand the blueprint for building reliable nanotech on gold. It is just such an incredibly elegant solution to a decades-old mystery. But I do want to leave you with a provocative thought before we wrap up. Now that we conclusively know the staple motif rules how molecules dance on gold, what other nanoscale secrets are hiding on the surfaces of other metals? I mean, if gold is dynamically pulling atoms out of its own surface just to build molecular staples, this might just be the very beginning of understanding how we can unlock and eventually manipulate all metal surfaces for the technology of tomorrow. Thanks so much for joining me on this explainer, and definitely stay curious.